Chapter 11, Section 11, we're modelling with differential equations, and this is another one of those modelling sections of the chapters where really what this is take what we know so far and apply it. So there's not too much to say in terms of new techniques, but a few things to point out. First of all, we're combining, as we often are in the modelling sections and towards the end of the chapters, we're combining things that we know. Obviously, we're taking section 10 of chapter 11, solving differential equations. So once we've got the differential equation, we're going to have to solve them at some point here. But we're also using the last section, I think it was, of chapter 9. Yeah, so the rates of change, okay? So those techniques there might be worth a recap before you delve into this section. Only two other things to say, really, because most of what I have to say is recapping those things. It's quite common you get a differential equation of this sort, and if you look at the solution is going to be that, okay? So it's just worth looking out for those sorts of things. dp, but so d something by dt, it's almost always dt in these kind of questions, is a constant times whatever that thing is there. And the solution is of the form e to the kt times by something else, okay? We often call it ae to the kt. A capital A is often the letter that we use for that thing in front. So once you've been through this example here, you should be kind of used to that. Now, if this was an exam that involved loads of differential equations, we could probably almost use that result, p equals ae to the kt, without having to show any working. Probably, though, I wouldn't do that in an A-level exam. I'd go through the steps to show how you get to the ae to the 3t, because that's what they're asking you to do. All we have to do is solve these differential equations by separating the variables. Let's actually separate the variables and integrate carefully. The other thing is, let's just have a look at example 28 quickly. We've got this water tank. I'll let you pause the video and read it if you want to. We're asked for dH by dt. Now what we have in this case is we've got V, and it tells us that the rate at which this water is flowing out is proportional to the cube root of the volume, okay? So we know something about V and H. We know our V and H are linked because we've got the formula. And we know something about how V and T are linked. So we're back into that technique from the end of chapter 9. dV by dH is something that we can find. dV by dt is something that we can find. But what we want is dH by dt. So we're going to go for dH by dt equals dH by dV, dV by dt. And how do we know dH by dV? Sorry, I'm getting off the screen there. So dH by dt is what we want to find. How do we know dH by dV? Because it's 1 over dV by dH, and that's one of the things we know. dV by dt we can work out because they tell us that dV by dt is proportional to the cube root of V. So it's a combination of writing the differential equation and using that technique for sort of combining things via the chain rule. Now, if that seems a bit quick, go back and check the section from the end of chapter 9, because I do it in quite a bit of detail there. So that's the end of chapter 11, section 11, which may be the last section for you, depending on where this parametric curve stuff falls in your particular book. So good luck with that section, or possibly good luck with the whole of integration.